Hello, my name is Craig Otto. This is Statistics for SPC, Operational Excellence, and today we're going to get into the third part of hypothesis testing, one of the most challenging yet most exciting parts of hypothesis testing. And you're going to say, yeah, right, Craig, good one. But hopefully I got some good examples for you today. I think they should help us better understand which hypothesis tests to use. And the good thing is, you should have your handy dandy calculator to help you do all that complicated math for you. And as my high school teacher always said, push the button and out comes the cookie. Um, you're lucky you don't have him, because he would be making you do all this math by hand and understanding how it all comes out. So I'm going to be a little bit nicer than he was. I'm going to let you allow you to use your calculators to find the answers. So with that, let's go ahead and get started. I have two examples here, and I'll try to make sure I have these links on our Angel so that you guys can get in and check those examples out here. What I'm going to do is I'm going to go through one website. Actually, it's the same website, just two different web pages. One goes through the Z-score test, and the other one does the t-test. Okay, so we have different examples here. I'm going to jump over. Here is the Z-test, as I mentioned. And what I wanted to, the reason I show this is because I want you to know how to type it in on your calculator. You're going to find that it's fairly easy, pretty straightforward. As I said, it makes it a lot easier than you having to crunch the numbers. So, with that, got an example here. Sample size of 200 has a mean of 20. Assume that the population standard deviation is 6. Okay, so they're kind of giving us givens here. Alright, so let's say we want to test the hypothesis that the population mean is not different from 19.2 with the level significance alpha equals 5%. What that means is this test is going to be for 95% confidence. Okay. Alright, so let's go down here. So the way that we have to do this is we have to press the stat button, okay, on our calculator, and arrow down to or arrow over, I should say. When it comes up, it'll probably be on the edit. Just arrow over to what's right here, test. Okay, and then what you need to do is it'll likely already be on the Z test. That's the first one. So what you do is just hit enter. Okay, and what all these other ones are all the different types of tests. Remember the last time I showed you all those different tests, and I said, well, you know, this session we'll go through and figure out how to use them and when to use them. So that's what we're doing now. So I'm going to show you just first with this calculator, the Z test, and then I'll get into some better examples than this one. This one's just boring. I don't like examples like this. So, and you'll see what I mean here in a second. I try to come up with some more practical examples. But okay, so when you hit enter on this Z test, you're going to have two different options. One is you can use the data option or the stats. Now, I was very nice to you. You can thank me later. I'm only going to make you put stats in. Okay, I could make you go into the lists and enter all this data for two different populations, and then you just have to hit this data. But in all my examples, all the quizzes, all the tests, we're only using stats. Okay, and that kind of makes it easy because what we're doing is just plugging in the givens. Okay, so like in our example, mu sub 0, what that means is that's the historical mean, and up here that's 19.2. Okay, so what this is saying is in the past this process has ran 19.2, and we have a sample of 200 though that was averaging 20. So that's different than 19.2, right? But how different is it? Is it statistically different? That's kind of what we're trying to find out. Okay, so what we do is of that sample that we chose, the sigma was 6. You can see that standard deviation was 6. We had an average or x bar of 20. So see, mean of 20. And a sample size of 200. Okay, so sample size 200. That's where they get that from. All right, and in our example, we just want to know is it different with is not different. See, alpha of 0.05. Okay, and that alpha you don't need to put in. That's just something that we need to know when we compare p-values. Right? We spent some time last time talking about p-values, so that's why that alpha is important. All right, so once you select the not equal, as in our case we're doing a two-tailed test, so that's why it's not equal. All right, and then you hit down to the calculate area here, and you press enter, and it will shoot some information out. Okay. All right, so the results, p of 0.1. Okay, 0.1. Now remember from our example last time, we wanted a level of significance of 0.05. So alpha was 0.05. 0.05 is less than, your critical value is less than 0.1. So that means it doesn't fall within that critical region, right? It's outside of it. So what that means is with that percent level of confidence, we can say that we fail to reject because our p-value is not less than the 0.05. Okay. All right. Same thing can be done. They go through, and certain times you might have two different populations. Okay. Two different populations with data, and you want to know, are they equivalent? So you have a two sample. You see how they did that? A two sample z-test where you had two different sets of data, and you want to compare those, right? Because last time we only had one set of data. We compared it to a population mean. Okay, and the reason we're using a z-test and not a t-test is why? Well, it's because we know our standard deviation. All right. So then they plug you plug the data in, and you can see like the standard deviation 1, standard deviation 2, mean 1, mean 2, sample size 1, sample size 2. What that is you just got to make sure you don't mix your numbers up. Everything from the first sample gets plugged in under the sub 1s, so the sigma sub 1, the x bar sub 1, and the n sub 1. And then the second set gets plugged in under the second, or the sub 2, right? Choose your, in this case it did another two-tailed test. So they selected that one, you hit calculate, and it pumps it out. Uh-oh, now we've got a p-value of 0.01. Okay, that's significant. That's where we reject the null hypothesis, because it's less than that 0.05. Okay, it fell within the critical region. So we reject the hypothesis that the sample sizes are equivalent. Okay. I'm not going to get into all these, but I highly encourage you to go down through and just try some of these. Again, it's just, here we're doing the proportion, and with proportions it's just plugging and chugging again, knowing what your x is, knowing what your sample size is, and knowing what your historical mean was. Okay, so all of this can be done in the calculator, and it gives you multiple examples here, so I highly encourage you to finish those out. The same website, different web page, the t-test, same thing. All this information can be typed in. You just hit the calculate, and it plugs and chugs and spits out the number. So like here, this p-value of 0.005, it's less than the 0.05. That means we reject. See, reject the null hypothesis. Scroll down here, and then here you have two small samples. Okay, so you comparing two. That's where you go to two sample t-test. Okay, and again, plug in the numbers. Look for that p-value. So a p of 0.384. That's much bigger than 0.05. So we do not reject. It's not within the critical region. We do not reject the null hypothesis. So you can see how this works. And I mentioned, sometimes you have data, and I told you I wouldn't make you plug in the data and do it. So this is just an example, though, of one that had data. You can see instead of using stats, you just use data, select the list that it comes from. So I think these two web pages are very good, at least helping you with the calculator first on. But the examples, in my opinion, are kind of lame. So let's show you some better ones. Okay, so z-test. Here's an example. Okay, local baseball team has an average strikeout rate of 7 strikeouts per 9 innings with a standard deviation of 1. Okay, in the current season, the strikeout rate through 45 games has been 7.2 per 9 innings. Is the current baseball team striking out more than the historical teams with 90% confidence? How about with 95% confidence? Okay, so let's see. Basically, for a z-test, I've kind of highlighted in here the numbers that we need to know, right? Like the 7 strikeouts per 9 innings. That's what it's been over the last few years with that standard deviation of 1. And then through the first few games of the season, they're striking out a little bit more, 7.2. Is that significant? So what we're stating is, remember, the null hypothesis, or H sub 0, is always that they're equal. That this 7 is equal to this 7.2. Okay? What we're trying to prove is this, 7.2 greater than the 7. Okay? So we have to plug in our mu. Our mu would be 7. Our standard deviation would be 1. Our current strikeout ratio, or X bar, is 7.2 with a sample size of 45. Okay. Now let's do the z value. So before I get to that z value, what we want to do is plug this information in on your calculator, right? You went to stats, you scrolled over to test, and you open up the z-test. And what you do is you plug this information in right here. And then you make sure you have the greater than test selected, and you hit the calculate button, and it'll give you this z of 1.342. Okay? And what it does is it converts that's your test statistic. It converts this into a p-value of 0.0899. Okay? So with because it's a one-tailed test, with 90% confidence, our critical value is 0.1. Okay? 0.1 for 90% confidence. It's just 1 minus the 90%, right? 1 minus 0.9 is 0.1. So that's our alpha. Now, 0.0899 falls within that critical region, if 90% confidence is what we're talking about. So in that case, for the 90% confidence, we would reject it because it falls within that critical region. Now, if our critical region was 0.05, for 95% confidence, now it falls outside of that, right? Because 0.08 is greater than the 0.05. So we would fail to reject. So you can start to see how critical. That's why when you choose your confidence interval, you have to choose it before you do the test, because depending on where it's at, it could be the difference of rejecting it and failing to reject. So what you tell the baseball team is, with 90% confidence, you are striking out more. But with 95% confidence, you can't necessarily say that. You fail to reject that. So you see, it's a big difference knowing, which confidence interval you choose. So how about a 2-sample z-test? All right. Let's say there's a machine that produces parts with a critical dimension averaging 2.21 and standard deviation of 0.5 out of 49 samples. So we just pulled 49 samples off the machine. It averaged 2.21 with a standard deviation of 0.5. All right. Now we need to run the same parts on a different machine because we've run out of capacity, and we took some data from that second machine, and the sample was averaging around 2.43, standard deviation 0.7, and that was on 45 samples. Okay, and what we want to know is, does the first machine run less than the second on the critical dimension? Okay, so does this first machine, does a 2.21 run less than the 2.43? Okay, with 95% confidence, and then we asked also with 99% confidence. Okay, all right, so we have to state our hypothesis, and this is a 2-sample, so the hypothesis is that the first sample is equal to the second. The alternative is that the first is less than the second. Okay, makes sense. And then we have our givens, right? We have our 2 sigmas. We have our 2 not standard deviations, but we have our 2 means, right? I'm just pulling these. Notice the color coding. I'm pulling it right out of the example, so you can see right where it's coming from. And then the 2 sample sizes, right from the example. Now when you plug these in on your calculator, remember, we go to stats, we scroll over to test, we scroll down to the 2-sample z-test, we hit enter, and then in there you should see all this information that we got to plug in. Okay, so go ahead and take the time to plug that in, and then at the bottom we have to choose our appropriate mu is less than mu2. Alright, and then you just hit that calculate, and it'll come out with a z value of this negative 1.7. Okay, and then what it does is, that's our test statistic. It converts that statistic into the p-value by finding the area under the curve, and it comes out to be 0.04. Okay, now we compare that. If 95% confidence is what we're talking about, 0.04 is less than that 0.05, so it's within the critical region, right? It's less than 0.05. It's within the critical region. That means we reject the hypothesis. Now, can we say that same thing for 99%? No, because the p-value for 99% is what? Or critical value. It's 0.01. P is greater than 0.01, so we fail to reject. Again, just being aware of what our confidence interval is and what our level of significance is. Okay, let's get into proportions. One proportion z-test. Okay, the proportion defective for an assembly line is 9%. The last 182 products off the line yielded 9 defectives. Does the recent yield represent the historical defect rate with 90% confidence? How about with 95%? Okay, so let's go ahead and get dug in here. So historically, we're going to say that the historical proportion defective is equal to the current, right? H sub O is always that they're equal. H sub 1 is that they're not equal. Okay, that they're not equal. Alright, so it comes out, you have to put in a P, historical P of the 0.09, The X value is 9. That's the number of defectives here, 9. And then 182 was the last sample size of products. Alright, so you plug that information in. Again, you go to Stats, scroll over to the test, go down to 1 proportion Z test, hit enter, put in your knowns here, select your historical P is not equal to your current P, and as your alternative, and then you hit calculate, and it should give you a Z value of minus 1.9. Converts that to a P value of 0.0495. Okay, so basically what we got here is, because it's a two-tailed test, we have the 0.1, 90% confidence, 0.1, but then you have to divide it by 2, so 0.05. So for this first one, is the p-value less than 0.05? Yes, it is. So we should reject the null hypothesis, right? Now, 95% confidence, it's going to be rejected too, because remember, 0.05 for 95% confidence, actually it should be, if we look at it, because it's a two-tailed test, your 95% confidence, 0.05 divided by 2 is 0.025. So 0.025 is your critical value. So in that case, we would fail to reject in that particular one. So you caught me. I need to change that. That's a 95% confidence. We would fail to reject because your critical value is that 0.025. Okay. The 2 proportion Z test. Okay, in the medical field, top box scores on a customer survey are considered important to patient satisfaction. Currently, there have been 27 top box scores out of 49 surveys, and the previous day there were 18 top box scores out of 45. Okay, so what I want to know is, on the current day, statistically, are we having more top box scores than the previous day? With 95% confidence, and then with 99% confidence. Okay, so again, our null hypothesis is that they're equal. Alternative is that one is greater than the second. So we go in and we go to Stats and select our test. Go down and select 2 proportion Z test. Hit enter. We'll plug in our knowns here. We have our 2 different x's. One is 27, one is 18. And our sample size for the first survey is 49, 45 for the second. Okay, we hit that information in, we plug it in, hit calculate, and you should get a Z value of 1.46. Okay. Now p-value of 0.07. Now with 95% confidence, again, 0.05 is our critical. We would fail to reject because p-value is greater than that. Now for 99% confidence, should be the same. Fail to reject because 0.07 is greater than 0.01. So pretty straightforward stuff. Again, it's nice because the calculator does, back in the old days, I would have to be calculating this test statistic using all them formulas. So calculator makes this a heck of a lot easier. Okay, t-test. Let's go ahead and do one of those. A local farmer has kept the yield records for his wheat for the last 5 seasons. He's seen an average of 55 bushels per acre with a standard deviation of 6.5. Okay, the average bushels per acre has been 65 for this year, and the farmer wants to know, is there a statistical difference in the yield with 90% confidence and then with 95% confidence. Okay, for the t-test, then we'll want to scroll over to the test from the stats menu and go ahead and scroll down and find the t-test. For our initial null hypothesis is that they're equal, and we have the null. Obviously we just want to know if there's a difference, so that they're not equal. Okay, and our mean of 65, that's taken from the average bushels per acre here, and our standard deviation 6.5, 55 bushels per acre, and that's out of the last 5 years. Our sample size was 5. So we go ahead and plug that information in, and we should hit calculate, and out comes the t-value. Okay, the t-value will be negative 3.44. That corresponds to a p-value of 0.026. Okay, now keep in mind this is a two-tailed test, so this can get tricky. With 90% confidence on a two-tailed test, that's 0.1, but then you divide it by 0.05, or divide it by 2 to get 0.05. Okay, so your critical value is 0.05. So for the first one, for 0.05, you would reject that because it's less than 0.05. Now, for 95% confidence, again, two-tailed test, so it's 0.05 divided by 2, so 0.025. And it's just barely greater than 0.025. So for 95% confidence, we would fail to reject. Oops, that should say fail to reject down below there. So fail to reject on that one. I'll make sure when I print this out, it's updated and corrected for you guys on Angel. Okay, and last one, this is the two-sample t-test. A brother and a sister, they're arguing over who's smarter in school. Okay, the sister is averaging a 91% with standard deviation of 5.5 on 9 of her exams. Okay, the brother is averaging 89, so two less, with a standard deviation of 2.7, and that's on 5 of his exams. The sister claims that she's smarter, but is her claim true with 95% confidence? How about with 99% confidence? Okay, tricky, tricky, tricky. Okay, so let's go ahead and go into our calculators, scroll down and find the two-sample t-test and select that one. Our null hypothesis is that they're equal. Brothers and sisters scores are equal, and the sister's claiming that hers is better, so that's it greater than. Okay, so standard deviation sub 1 for the brother, or for the sister, excuse me, was 5.5. For the brother was 2.7. Okay. For the sister, she's averaging 91. For the brother, 89. Okay, so we'll go ahead and plug those in. Sample size for the sister was 9 tests, and 5 tests for the brother. Okay, so you plug this in, and the parents ultimately find out who's smarter or not, right? You get a t-value of 0.91. 0.91. So that's a p-value of 0.19. So unfortunately, the sister is going to struggle proving that she's smarter with any level of confidence, because that's a larger p-value. So you'd fail to reject with 95% confidence, and you'd fail to reject with 99% confidence. Because p-value is significantly larger than either of these 0.025 and then 0.005. Remember, or no, excuse me, it's a one-tailed test, so 0.05 and 0.01. Okay, so with that, that's a lot of information to go through. Go ahead and use the quiz as a way to get better at some of this. Again, it's just a matter of plugging in the numbers. And when you do this, like if you're doing a problem and you're not sure if it's the right one, there's a good chance if you chose something in the calculator and that doesn't have all the givens, it's a good chance that you probably chose the wrong test in the calculator. So it's just a matter of going back and finding the right test based on the givens that we have. Okay, so go ahead and give that a shot. Don't be afraid to go back and watch this as examples and compare to what you have on the assessment, and just work your way through it. It'll take some time, but the more you do it, the better you'll get at it. Okay, thank you.